laser pulse ablation. They can be synthesized with uh, uh, flash method, energy flash method. They can synthesize with all techniques that we discussed in the previous lectures. Imagine we have some of these nanoparticles separated in the or liquid. There are two questions to ask. One is that how we can separate the liquid and nanoparticles from each other. The second question is that after we separate them, how we can separate different size of nanoparticles. Okay, these are two important issues. We want to separate the liquid medium from our nanoparticles, solid nanoparticles. Secondly, how we can uh, separate different size of nanoparticles. So this is important process. You need to know it very well. Imagine the nanoparticles in your bottom in your bottle or in your vessel is a small particle, but it has a higher volume than your liquid. So if you start to rotate the bottle, what will happen is that there will be a centrifugal force equal to F imposed to your particles. So your particles start to get a centrifugal force if you rotate your bottle. And as the larger M will be, there will be larger force. When you do not shake your particles, you just have your particles in the your vessel without any shaking or without any changing. Uh, the gravitational force will be on your particles. So um, how we can measure the gravitational force? If you have the mass of your nanoparticles have gravitational gravitational force on them. So your nanoparticle will feel some force because of the uh, because of the airs. But since the mass is low, they won't go to the bottom of your vessel, generally speaking. So that's why we need to increase this G force. Okay, and the way to do that, if you have the large particles, okay, if you have large particle, after sometimes the particle will sediment or precipitate in the bottom of your tube. Okay, the reason is the gravity. The reason is the gravitational force of Earth imposed on your uh, particles and your vessel. But admit, but if you have a small particles like nanoparticles, to sediment your particle in the bottom of your vessel, you need to increase this force. The way to increase it is basically is rotation. So you need to rotate your nanoparticles vessel in the way that the gravitational force will act on I'm sorry, the centrifugal force start to act on your nanoparticles, and as higher speed you rotate them, there will be higher rate of sedimentation of your nanoparticle in the bottom of your vessel. Usually, We do it with the tool which we call centrifuge. So basically, what we will do is we start to spin the bottle of nanoparticles and liquid, just like the medical labs do with the blood or body serum. So they rotate them in a machine which called centrifuge, and the particles or blood cells or heavier particles will go to the bottom of the your tubes, and the liquid will remain on top. Then you can get rid of the liquid out, and then you have your particles or cell in the bottom of your vessel. This process is quite well known, but the point is that when we do it for blood or other kind of particles in liquids, it's much easier to sediment them because they're large, so their mass is high. So with the lower centrifugal force, you can separate the cells or solid particles from your liquid. But when we have a small particle, like a nanoparticle, 10 nanometer, 20 nanometer to 100 nanometer of particles in your liquid, you need to have much higher centrifugal force. So you cannot change the mass, so you need to change the speed. So you need to rotate them with much higher angular rotational speed, or uh, what we call omega. And then you need to do it in a longer time period. If for blood cells, you do it in 1 minute. For nanoparticle, you need to do it 5, 10, or more uh, duration of time. Then your particle will sediment uh, on the bottom of your tube. Usually, by sedimentation is done first for the heavier particles. So if you start to rotate some suspension on a particle, first at the beginning, the heavier particle will sediment. So if you do it at the first minute, and then separate after first minute of rotation, you take out your sample. Okay, you get out your liquid, your material. Then you will see that there are some particle at the bottom, which is larger uh, particle at the bottom of your vessel, and you can put out the liquid. You can put out the liquid and continue the. You can put out the top, and you will have some liquid on the bottom. Okay, this is the large particle. Then you will continue on the rest for 5 more minutes, 10 more minutes, or 2 more minutes. Then again, you will have some sediment and some top liquid. You uh, take out you pour out the top, and then separate the bottom and centrifuge the top again. And then you can have, usually the smaller particle tend to sediment later by centrifuging. So you can separate basically your nanoparticles. And your smallest nanoparticle will sit down latest. So as heavier they are, they will sit down at the beginning of processing, and as small they are, they will sit down, sediment down later and later. So this is the way to separate the nanoparticle easily. And this is very important method because if you want to do any change in your solvent or in your uh, with your material, you need to wash the nanoparticle. What is the nanoparticle washing? Is basically centrifuging your material, and after the centrifugation, taking out the liquid medium, you can put out the new solvent. The new solvent can be ethanol, can be methanol, can be water, or whatever you want to have as a new solvent. Because sometimes you synthesize nanoparticle and in a medium, and you don't want to have that medium. You want to get out the solvent. And you add the new solvent or new liquid medium. The very important thing is that you should not leave the nanoparticle to dry. If nanoparticles dry, they will stick to each other and they are not nanoparticle anymore. They're called agglomerate. They're if they dry, they will stick to each other. So you should always keep in mind to have your nanoparticle separated from each other with a liquid. So you have, if you want to have nanoparticle as a nanoparticle, you should not let them dry. If they dry, they probably stick to each other. They are not nanoparticles, separate nanoparticle again. So they can be powder or whatever if they dry. So we want to keep them wet when we want to use them. And after washing or separation, we can work with our nanoparticle. So this was the first part of today's lectures. The second part will be about another but top to bottom to top method for synthesizing of nanoparticle. If you remember, I told you that nanoparticles are grown either by top to small, top to bottom, or bottom to top uh, methods. So today I'm going to discuss about the first bottom to top method. So we will want to discuss the how we can synthesize nanoparticle from atoms and molecules. So imagine we have atoms and molecules, and we start from atoms and molecules, and we want to synthesize nanoparticles. So let me share this slide for you. So if you can see these slides, please let me know. Also here, also in the audio connect screen window. Okay, so I'm going to talk about the bottom to top methods. Can you see the slides? Can you see the slides?
Yes, doctor.
Okay. In this method, you start from atoms, ions, and molecules, and they the atoms, ions, and molecules they stick each other, react with each other with the controlled condition, and then you will have either nanometallic particles. Imagine you have the solution of copper sulfate, and you synthesize copper, metallic copper nanoparticle, or nano copper oxide, or nano copper selenide or sulfide. So these are all nanoparticle, but synthesized with a solution with the smaller unit cells which called atoms or ions. The way the atoms are stick to each other and grow to form nanoparticles is called uh, nanoparticle growth, or and if it's done very slowly, you can control it in the way that you will have nanoparticle. But if you do it very fastly without controlling, you will have a process which called precipitation, chemical precipitation. During chemical precipitation, your particles grow very fast. Okay, so when they grow very fast, they stick to each other, and finally they will sit or sediment at the bottom of your reaction uh, flask. So you need to control this reaction. You need to decrease the speed very low. You need to keep the condition close to the equilibrium. So it means that you need to do it very slowly. You need to control the thermodynamical parameter of your reaction condition. If you just add some sulfide containing ions in the room temperature to your mixture of to your solution of copper sulfide or sulfate in water very fastly, well, there will be a powder formed in bottom of your in the bottom of your beaker or your vessel, and that is nothing except copper sulfide powder. And it's not nanoparticle; it's powder. It's large particles. So we don't need that actually, and we need to do it in a very controlled way that the particles start to grow up, and they won't grow very rapidly. So you will have some particles with a certain size, for example, 10 nanometer, 5 nanometer, or 20 nanometer, and they won't grow more. If they grow more, they get fat and they get very heavy, and they will go down to the bottom of your because of gravity, they will go to the bottom of your vessel. So if we need to control this process, we need to study thermodynamic, because the way we control this process is by thermodynamics, controlling the thermodynamics of the reaction. So the thermodynamic of the reaction give us some idea to control the uh, speed of this reaction. If you do not control the speed of this reaction, then you will have not nanoparticle, you will have some powder of your material. So to control the speed, we will discuss the uh, what is affect the speed of this reaction and where we need to stop this reaction. So there are two parameters that we need to discuss. First is kinetics of the reactions, and secondly, the what is affected kinetics of this reaction, and when we want to stop this process is basically is uh, very depend on the thermodynamical parameter. If you imagine we have the if you have the size of your if we can have control over the size and the speed of the reaction, then we can have the control of nanoparticle. But if we do not have the uh, control of the speed. This speed will the size. Imagine we plot the size of nanoparticle versus time. This will go very rapidly, very non-controllably to the very high. So we do not have any control to a reaction. So you will end up to powder. Basically, you will have powder. Uh, the parameters you need to control is basically the thermodynamical parameter to control the speed. You need to go very slowly. You need to increase the size of your nanoparticle very slowly. And for doing that, for increasing the size of nanoparticle very slowly, you need to do one thing. You need to do one important thing. And that important thing is controlling some thermodynamical parameter. Thermodynamical parameter of your condition is temperature, concentration, pressure, which we do not change it too much. But let's go to the some brief overview of thermodynamics of grooves. If you remember when we study the thermodynamics of reactions, we are speaking about oh, where is it? Where is it? We're talking about the reactions, chemical reaction. We have two kind of reactions. We can have two kind of reactions. Yes. When we are talking about reactions, we can have two kind of reactions. We can have spontaneous reactions and non-spontaneous reaction, or or irreversible reaction and non-irreversible reaction. For a chemical reaction which happened spontaneously, there is a function which called G, or Gibbs function, which is basically defined as the heat of the system minus temperature of the system time to entropy of system, or S. So this is a definition of Gibbs reaction. And for a reaction which is goes spontaneously and happened, it happened can happen very fast. Usually, is release energy, and with increasing the disorder of the system or of the world, not the system alone. So I think you read this in the thermodynamics. For example, if you have some oil, crude oil, or some gas or oil, and you have some air in the surrounding, and you hit them up, and you ignite them with the sparkle or whatever, then you will have fire. And when the fire starts, you cannot stop it easily. So basically, this burning happens spontaneously, and they result carbon dioxide and water. And the Gibbs energy of the system is reducing down. And if you have carbon dioxide and water together, and you wanted to turn it back to the oil and air in normal condition, in the room temperature and in the ambient atmosphere, it's impossible to do that. So the G function is increasing. So systems, thermodynamical systems, tend to work in a way that their G function is reducing. So the fire is reducing the G function because the heat is releasing and also lots of gas is releasing, so the entropy is increasing, and also the heat will release, so the the delta G is below zero. So the system and free energy is reducing. But we have some conditions. For example, at 0 Celsius, 0 degrees Celsius, or 273 Kelvin temperature, and at 1 atmosphere, ice and water are in equilibrium. So the speed that the water is melting is equal to the speed that the water is solidified. So these two reactions happen in parallel with the same speed. And in this condition, we call dg is equals to zero. So this, and at exactly 1 atmosphere and 0 degrees Celsius, we have these two phase of material in equilibrium. So if you're in equilibrium, you can control the things because the speed is low. So by changing a little bit of temperature, a little bit above the zero, just epsilon amount of the temperature above 0 degrees Celsius, the water starts to melt. It means that the speed of the melting is higher than the speed of solidification. And if you reduce down the temperature just epsilon degrees Celsius below the 0 degree Celsius, the water start to solidify in a little bit higher speed. So will your piece of ice will grow up. So this is what I written here. When you increase the temperature, the melting will happen just a little bit, and if you increase the temperature, the growth will happen. And close to equilibrium, you can control where to go. If you change this condition very dramatically, your system will escape from the equilibrium condition, and you do not have any more control on your growth parameters or your growth speed. So you suddenly will form lots of ice, or your water will melt quite fast. So you need to study the process which your nanoparticles or particles are formed. If you study them, or at least you uh, study different phase that your particles start to form as a cluster, and then nuclei, and then nanoparticles, mainly if you start to solidify, or you start to study the growth condition, you will see that by at the beginning of your growth, you only have cluster. You don't have any particle. You have something which is called cluster. If the cluster go a little bit, the cluster is not something which is stable. Clusters are not stable. The clusters are called nuclei. So they can turn to the nanoparticle, or they can dissolve in your vessel. So basically, what you have here at the beginning or at the uh, start point of your reaction is just a nuclei for your nanoparticle. And if your nanoparticle is formed, they can stay in that size. The nanoparticle can stay in that size. Then you have the stable size, or you can change the condition, or your condition can be in the way that you're far away from the equilibrium, so they will turn to the large particles. So if we draw a g g function over the size of your nanoparticle, over the radius of your nanoparticle, we see that at the beginning the particle start to, when it grows as a cluster, first they start to grow, and at a certain radius, or which what we call r star, it has maximum g function. So then if the temperature increase, if the size increase a little bit, so the g start to reduce. So at the beginning the g is increasing, so the system start to turn from the stable condition, which is g 0, to a non-stable condition, which is called g star, and then it can come back to the stable condition again, which is called nanoparticle. And if you continue to grow your particle, then the g start to decrease more and more. So this is where we call the equilibrium size, or the size of your nanoparticle. Here, GSR is the cluster size, or nuclei, the size of nuclei. Now we want to study this. We want to calculate how will dg change by increasing the size of a spherical nanoparticle to r star, and then how it will change to r0, and how we can play with the thermodynamical condition like a temperature or concentration in the way that you can control delta G close to zero, and then close to, and then close, and then goes to uh, at the beginning 0 and r star. So first we need to calculate the delta G of formation. The delta G of formation uh, is the amount of energy is needed or released, or the free change in the free Gibbs function when you have one mole of materials. Okay, when you form one mole of NaCl, any solid, when you form one mole of copper sulfide, any phase, if you form it one for one mole, we call it G formation. The unit of the G formation, delta G formation, is joule per mole. And the other parameter is molar volume. Volume of your material means that how the molar volume of material is basically is how big, how what is the size what is the volume of 1 mole of your material. So basically, if we have density of your material, we have rho, which is m over volume, mass over volume is equal to 1 mole. In 1 mole, your mass is equal to molar mass of your material. Okay, and when you have the molar at molar volume, the volume of your 1 mole of material is mass of your material over the density of your material. Volumetric G or GV is the ratio of the G formation over the molar volume. So if you have 1 mole of your material, the amount of energy is released, the amount of free energy, change of the free energy or G function over the volume of it, is called volumetric G or GV. Um, and it shows by the minus. So we put a minus on that because for formation of most solids, the delta G is minus. So we need to make it positive. So in this way, for most solids, or basically stable materials, the GV is bigger than zero. So I suggest we took a break. Okay, we will take a break, and then we will come back after, let's say, 15-20 minutes. We will
Okay,
discuss.
doctor. Okay.
Yeah, we will discuss about another parameters of groups. Okay.